Now, the second application of gravitational lensing is in determining dark matter. So again, dark matter we cannot see in our universe. So the only way to figure out where it is by looking at its effects. Now, what you can do is that, if you remember, I talked about cluster lensing, where you have clusters of galaxies, all of which have large amounts of dark matter in them. And what you do is you take the observations of the lenses and then you create computer simulations which try and replicate the structure of mass, the distribution of mass you would need to create that lens. And this way you sort of successively iterate through different configurations, and what you end up with is a fairly accurate map of the matter distribution of a lens. Then, subtracting out what we can see visibly, we can get a map of dark matter. So that's sort of a basic introduction to gravitational lensing and some of its applications. Do you have any questions?
So that picture that has become so famous of the dark matter, was the dark matter map that was made through gravitational lensing?
I believe that was one of the tools, yes.
Okay.
That map is, it's a simulation. It's not actually necessarily what's exactly out there, but it's a simulation that effectively reproduces the lensing that we see of distant galaxies.
Yeah, not really a question. I thought that went really well, but one of the nice things that you can do, or that they have done, is in the 70s they put accurate atomic clocks on planes, and as you move the planes, there are two corrections to time. One comes from special relativity because you're moving, time slows down. Yeah. The other one comes from gravity. Right, and they calculated that in the theory matches the experiment. So you can actually observe these changes using very accurate clocks with, not every day, but every year, scales of
there's also
motion.
You can leverage the fact that we're moving around the sun,
yeah.
And so we're moving into two different places in space, and you can use, it's called parallax, to determine distances and things like that.
So you can find relativistic effects at very low speeds?
Not very low. I mean, it's still there.
But like our planet around the sun, you can find out a relativistic effect of that.
We have, if you're doing anything with GPS, any GPS satellite has to take into account relativistic effects, because otherwise your GPS is broken.
Every GPS satellite has 3 atomic clocks, and their accuracy is billionth of a second. So
otherwise,
that's how it works. We actually just had a lecture on GPS last Friday. So.
The Apollo 11 astronauts, I think, lived many millions of a fraction of a second less than what they should have because they went so fast.
Wouldn't they live longer because they're going faster?
Whatever.
Yeah.
It depends.
Time slowed down.
How high you are.
It's true.
So you could find a a reference frame, like a zero motion reference frame?
You cannot find a zero motion reference frame. That's the whole problem. Is that there's no special frame of reference that we can use for zero motion. There's a special state of zero acceleration, so free fall or microgravity, but because of the, especially with light is the big problem, is that there's no sort of zero that you can use. Because of changes in time.
Correct.
Excellent.
That's why they call it relativity, because there's no such notion as absolute precision or speed.
Yeah.
But we always just approximate for whatever scenario because it's so many in most cases.
Normally, you just pick an object and say, oh, that object is not moving. Yeah. But really what you're saying is, I'm going to take all my speeds to be referenced to whatever speed that object is.
From gravitational lensing, I would expect a blur, a much more fuzzy effect than something as so well defined as we see here. Because they're just random masses distributed like as a blob?
To be honest, I'm not sure why you get such clear images. It might have to do with the fact that the matter distribution is fairly. I would guess that it's fairly even. When you're talking about the scales that they're talking about. But like, yeah, you do get these arcs of fuzziness. But sometimes I guess the lens just lines up right. Anything else?
Is this how they detected black holes, or is there another?
You could use the same micro lensing that we use to detect star systems and planets to detect the black holes, because they have gravitational wells. That's the whole point. That's the reason why they're black holes, is because they draw the light in. So they do have a gravitational well which will bend light around it, as long as the light doesn't go into the black hole.
So you would be able to see a star, but then it's not positioned there.
How it works is that you've got you've got Earth here, you've got your galaxy or your star over here, and then you have a black hole which moves like this between them. And so when it's here, it's going to bend the light around it. And so you can see the effect, the change in light because of that bending. And then the black hole flies away. So it's not useful for actually then saying, okay, I know there's a black hole here, now I can go find it, because the black hole's gone. But what you can use is you can use it to sort of see the distribution of how many black holes are there in the universe by doing statistical studies and things like that.
Cool, great, thanks.